So, this is a review for the test. We're just going to kind of go through the review sheets that are posted, maybe ask any questions, but I would say more important for you guys is to compare what you wrote down, or if you didn't write anything down, then I mean, that means you haven't thought about the topic, and what you need to do is be kind of, this is what I know, and then compare to or show me and say, hey Jay, did I get all of it? I can tell you the bare minimum, like that I consider the basics, as in things that reminds me, or this is the trick I use to remember something. But in the end, you and I are different, and I have a lot more background, so I may not need to have as much info. But like for instance, if we start off just on the study guide, we're starting off with energy. So what can you guys tell me about energy for this next test? You don't have to quote numbers, you can make vague statements too. But I mean, there was a homework question, for instance, on at least 2 out of the 3 homeworks, I think, on it. That's last semester. So we're talking in respect to lipids and amino acids and carbohydrates. So one of the things we talked about is the energy content of carbs versus lipids. Does that ring a bell in anyone's brain?
Yeah.
Which one has more energy? And see, this is also levels of detail. The first one is simply, to have an understanding that we use both of these for food sources, right? So energy means it's a food source, or we use it as a means of generating energy. And technically we can throw amino acids up there, but they're not primarily used for energy generation, even though they can be. In fact, I was reading some weird stuff saying that, it's better to eat certain things, and I don't know. I'm not going to worry about going into details. We're going to try to stay focused. So which one has more energy, carbs or lipids? So lipids generally have about 9 kcals. I think it's per gram, but I would have to look up the exact number. That's where I get a little lazy. I have the exact number written in my book. It's probably something that you should probably put up. But I know it's a relationship of about 2, meaning lipids have twice as much energy as carbohydrates. And I guess we can actually either look up the value in the notes, or certainly it's contained in your book. Maybe we can even put some references down to where we're at. We're kind of skipping over some steps. Yeah, 9.5. Oh, this is 9.5. See? I'd accept 9. And the other one is doesn't tell. It must be in the carbohydrate chapter. We'll just go with that and be close enough. So lipids have more energy than carbohydrates. Why? See, that's the next level of statement. So if you can say the very first part, which is simply, one has more energy than the other, well, that's probably maybe worth a point or 2 on the test, but probably associated with that is going to be the question of why.
Because of their structure.
Yeah, there's something to do with their structure.
It has 3 carbohydrates or carboxylic acid groups.
No, it has nothing to do with really, well, go ahead, finish your statement, actually.
Because there's 3, I guess, tail kind of things that attach.
Well, I mean, we can look at the basic structure like this, right? So, I mean, that's the basic structure of a lipid versus a carbohydrate, which, has a bunch of OHs, right? And certainly this is not one of the ones we use for energy, but to illustrate the point, it is, I hope, sufficient. You'd think I'd just memorize what the structure of glucose is, but I'd probably push out something really important. So, yes, it has something to do with the structure. What about it? So this is where I think the study and the review sessions will be more useful if you've got that information and you've already gone through it once, because then you're going back through and filling in the gaps. Right now, if you're really trying to learn it all from scratch, you might as well just go start watching the lectures again. So I guess I'm trying to transition you guys, and maybe we waited too late in the semester to do it. But I'm trying to transition you guys to the idea that if you study kind of ahead of time, then come and ask the questions to fill in the gaps, that's probably better than doing it. Or, you know, if you're trying to learn, essentially we started this, what, right after spring break, so like 2-3 weeks ago. You know, if you're trying to, between now and Thursday, which is 2 nights, learn 3 weeks worth of material, hopefully
It's more
it better be the
just
third time around.
material. Like, I understand it, it's just I don't remember it from the top of my head. But if I look
But that's
at
what a
it,
test is, right?
Well,
Test
that-
is from the top of your head is what I'm saying.
Right, that's why I have a couple of days studying it.
Okay.
I've studied for a couple, 3 days now.
Okay, so fill in some details. So these are about 40% carbon, 40% carbon, right? These are 70, come on, don't crash on me. Make my life easy. 75% carbon. So lipids are just have more energy in them because they have more carbons as part of it. And now, and I'm not saying that because, you know, this is a huge molecule, we're saying that if we compare like to like, meaning if we compare 3 glucose molecules, that's about the same as, actually no, you have to have like 9 glucose molecules to have 1 triacylglycerol. But if you're talking about just a fatty acid, you know, like this, these are on the order of 18 carbons for the normal one. It's the easiest one, and these are 6 carbons, right? So, you know, when we're making comparisons, we're building in that factor of 3 already. So even if you have 3 glucose molecules and 1 fatty acid, you still have all that more energy in the lipids because it's based on mass, right? And then what's the real key though? Meaning this reason's okay, but it's not it doesn't get to the heart of the matter. Yeah, more reduced, more oxidized. And so that means that we need to review, you know, like Leo the Lion goes grr, right? And what it means to be those. Do you guys remember the difference between oxidation and reduction? That's why being reduced, being more reduced, means you have more electrons, right? Electrons are how we exchange energy. Or at least that's how we store it. We store it in the chemical bonds that are the electrons. So that's why being reduced, gaining electrons, is storing more energy. What are some other signs? Because that's the definition, basically. What are some? Oops. Now I'm just reversing them. Lose bonds to hydrogen. So what that really says is that if I compare a carbon-oxygen bond to a carbon-hydrogen bond in energy, there's more energy stored in a carbon-hydrogen bond than there is for a carbon-oxygen bond, right? So notice that if I take a look at a fatty acid, and let's ignore the exception to it and take a look at the average carbon, notice that the average one is a carbon, 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 and it's got 2 bonds to hydrogen, right? But if I take a look at that glucose carbon has an OH attached to it, and then it's got bonds to other carbons, and it's got bonds to a hydrogen. So because this has more bonds to hydrogen, we say it's more more reduced. Or we could, you know, say that carbohydrates are more oxidized. The other way I like to think about it is methane is about the most compact form of storage you can have for energy because it's got carbon with 4 hydrogens, right? And then you've got a fat. Then you've got your carbohydrates, right? And then eventually, oops, I have these drawn the wrong way. this technically has more energy. At the very far end, CO2 is the waste product for most organic pathways, right? Or for a lot of organic pathways, because CO2 no longer has energy, so we just, once we've made the CO2, we expel it or get rid of it. We have no further use for it. Now, what about oxidation numbers? Do you remember the general rules? Now, one thing I should point out is calculating oxidation numbers might be in this chapter since we covered it, but certainly it's either going to show up on this test or the bioenergetics test or both. Meaning, I just randomly pick topics to put on the test, so if it shows up on both, great. If it shows up on one, great. It's going to show up on one or the other for sure. So what is an oxidation number? So it's a way of measuring electrons. So it's the fictional charge on an atom or molecule. And when I say fictional, it's because, for instance, Na plus 1, Cl minus 1, that plus 1 and that minus 1 are oxidation numbers. Those really do gain and lose electrons, right? But if I'm talking about a molecule like this, since I'm sharing electrons, they really don't gain or lose, electrons. And so that's what I mean by it's a fictional charge. What we're saying is that if hydrogen is always plus 1 and oxygen is always minus 2 for our simplified stuff that we're looking at, then we can say that carbon must be a minus 4 in this case, right? Because I've got 4 hydrogens at plus 1 and 1 carbon at minus 4. And so what an oxidation number is a way to kind of keep track of the electrons, and it's also kind of a way to keep track of the energy in it, and that the more negative this number is, more negative equals more reduced equals more energy. Because the other end of the spectrum is, of course, carbon dioxide. Notice in this case, if the oxygens are minus 2, the carbon has to be plus 4. And so our oxidation number scale can range from minus 4 to plus 4. And then, of course, in the middle, we have our fat, right? So actually, let me draw it out. So we have our typical fat atom. And so if this is plus 1, that's plus 1. Then each of the carbons has a minus 2 stuck on it, right? You guys, is this making sense? Seems familiar? Oops, let's do it this way since we normally draw them like this.
How do you just know that the carbon has minus 2 of each?
Because the total has to be 0, right?
Okay.
So remember, the sum of the oxidation numbers equals 0 for a neutral molecule. And so if there's 4 pluses because of the hydrogen, that means the carbon must be a minus 4. If there's 2 minuses on carbon dioxide, then that's minus 4, so the carbon to balance it must be plus 4. And so here, if you look, we've got plus 1, minus 2 for the oxygen. That means carbon is 0. One of the reasons carbon is probably the central molecule for life is it doesn't have d electrons, so that means its chemistry is pretty simple and pretty stable, and it forms the same things over and over and over again. And the second is because its oxidation number can range all the way from minus 4 to plus 4, whereas oxygen pretty much 99.9% of the time is minus 2. Same thing with hydrogen, 99.9% of the time it's plus 1, so it doesn't have as much variability that it can do. But carbon can make so many different things because it has that variability for the oxidation numbers. So most energy, negative oxidation number; highest energy, positive oxidation number. We covered all the signs. Oh, I guess we should go back. Let's add one more sign. If something is oxidized, that generally means that we lose energy in the molecule. And here the molecule gains energy. So if we're looking at changes, although I don't think in this chapter we'll look at changes, I'll throw that up as a fourth sign that's pretty easy to keep track of. Meaning if I have an exothermic reaction can almost bet that something's being oxidized. Well, maybe that's too broad of a statement. Okay, so that covers energy in these chapters, meaning we focused on really carbohydrates versus lipids, even though this is technically just the lipids chapter, right? And we'll go into more detail. We'll look at all the biological pathways. I shouldn't say all. We'll look at some of the biological pathways and see exactly how that energy is extracted. You guys covered the citric acid cycle in Todd's class, right? So I usually stick with beta oxidation. Did he cover that at all?
Isn't that the extra credit
That was one of the extra credits. It's one of those things where it would be nice if I covered the topic before you had to do the extra credit assignment, but maybe the extra credit assignment you'll be following along going, oh. We can only coordinate so much because, well, his textbook just covers it earlier than mine even gets close to it. So the next thing I have on this is reactions. And what we should realize is that we don't have just reactions for lipids, but we do have reactions for lipids, and we're also going to have them for the amino acids, right? So to me, the key thing to being able to study, to feel that sense of completeness, is how many different types of reactions are there that you need to know? I mean, I have 4 listed, I think, under lipids, and I think there's probably 4 more under amino acids. But there's 4, right, for the lipids. Can you name those 4? See, if you can name them, means you've kind of studied and you've already got a good feel for them, and you can figure them out. So you got hydrolysis. And what's the opposite of hydrolysis? And then what are the other ones? And then I just called it the bromine reaction. And so there seems like there's 4 reactions there, right? Yeah. And I guess technically we have dehydrogenation too. I don't remember. Maybe I should put hydrogenation, dehydrogenation. We'll just add that there too. And maybe I'll make a note and I'll add that to the study guide. Because I literally just went through my notes in the book and stuff, and so.
Is that the dehydrogenation, just like a subtraction?
Well, what it is really it's just the opposite of hydrogenation. I mean, they're all reactions you've had before. And see, what I want you to realize is that, like, for instance, the top 2 are just plus H2O minus H2O, right? Meaning they're opposites. If you know one of them, you kind of know both of them, right? At least that's my goal, or that's the hope. And then notice that hydrogenation, dehydrogenation, really is just adding H2 and removing H2. And also notice that bromination, or adding bromine, is just adding plus Br2. So really, if you ask me, you've got 2 types of reactions. Meaning if you can condense that information down and say, well, instead of 4 or 5, whatever number, however we want to label them, instead I only have 2 things I need to remember, great. And I'll be honest, if you can actually say, this is review of chapter, I want to say, I don't remember the number, but certainly the chapter on things like alcohols and carboxylic acids, right? Meaning, if you can say, I already know that shit, that's one less thing you have to study. That's why I keep kind of stressing, if you learn it and don't forget it, or at least when it comes to reviewing it, you're like, ah. Of course, you also have to make sure when you say, ah, that you can actually do it. Meaning, one of the flaws I find when people study is they have their pages on their notes, they read something and go, oh, that makes sense. But they don't approach it from the perspective of a test, which is, you don't have your notes. You can't look at it and go, oh yeah, that makes sense. You have to come up with it off the top of your head. So that's why I'm saying you can actually list the 4 or 5 types of reactions off the top of your head and write an example off the top of the head. You're going to ace that part of the test, right? If you look at your notes and go, ah, that makes sense. I don't know. I really can't predict whether, some people can really look at their notes and it'll stick. Some people can look at their notes, go, yeah, that makes sense, and they go to sleep, wake up the next morning, and it's gone. And so you need to figure out what a sort of person you are. Am I a sort of person that can just review my notes and do wonderful? Or am I a sort of person that, man, I better write down 5 examples of it off the top of my head so I know I really know it? And the other thing I really think comes from looking and drawing on a piece of paper, blank sheets of paper, is if you can do it, you feel pretty confident on the test, right? Because you just did it. How can the test be any harder? You did it with a blank sheet of paper without a freaking question even giving you a cue, whereas if you have to have that cue, which is the question on the test, or you have to be able to look at your notes to do it, which is one of the, and I know I'm getting preachy here, but whatever, it's supposed to be about how to learn too, not just learning. You know, if you can do your homework without looking at your notes, then that means you're really rocking. Now, if you do your homework and look back and forth at your notes, then you got to be, every time you look at your notes, you have to say, how am I going to remember this? You need to write it down again. Do you need to summarize it? Kind of think along those lines when you're studying. And it's kind of the difference between walking into a test and knowing you're going to nail it and walking into a test and not being sure how you did on it or how you're going to do on it. And to me, that sense of comfort and calmness is wonderful. So, give me 4 examples. What would be a good example for hydrolysis? Can you just come up with one off the top of your head? See, I'll let you in on a secret. Here's why I seem smart. Not because maybe I am inherently smarter than you guys. I have no idea. We'd all have to take IQ tests, right? So, who cares? I've done this for 10 years, right? But, I'll tell you what, even my first year, I knew most of it, right? But by every year, I refer to things less and less in the notes. And so, because I've internalized it all, right? So you guys can do that same process by saying, I'm going to remember one example. So what do you remember about it, if nothing else? Certainly, you ought to be able to go like this, right? I mean, can you think of anything? So remember that plus H2O almost always breaks a bond like this. And we can even do the next chapter and realize that, are those 2 molecules the same? Well, I mean, obviously they're not the same. One's got a nitrogen and one's got an oxygen, right? One's an ester and one's an amide, right? I guess what I'm trying to say is that reaction the same for both of them? Meaning, do you just go like this? Oops, I wanted to switch colors. Do you just go like this and go H, OH, H, OH? Ooh, I did it wrong. This is where Jay has to be paying attention. OH, H, OH. And so, when you're writing the answer then, since you know where the molecule breaks apart right next to that carbonyl carbon, you know that, you get carboxylic acid and alcohol, and you get, a carboxylic acid. Yeah, well, it doesn't matter if I draw it right. I'm not trying to keep track of number of carbons and stuff. What? No. But what I want you to also realize is if you can memorize or understand where, just if you know the fact where this occurs, right? Then when you switch...
I would be able to recognize it if I can't think of an example.
So what I'm saying is go that next step, if you can. Or... Yep.
So what if we just
But you should...
remember that hydrolysis goes to carboxylic acid and alcohol,
That works.
and dehydration would go to carboxylic acid.
No, dehydration is totally different.
Right.
So we'll get there in a sec. Oh, okay, it makes it. I thought you were saying dehydrogenation for some reason there.
Oh.
So I guess what I'm trying to say is, if you understand one, this one should be the same process, right? This one should be the same process.
You just turn,
Or,
isn't that, you just take the water higher, that's dehydration, you take the water
We can even do an ugly one. Oops. Oh no, that's right. I mean, it's just like an NH3 plus, and there's usually a minus sign in there. All those should be the same thing, right? You should hopefully start piecing together that I know I'm going to break it here, here, and here, right? Here, 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 here. And so, you know, you're going to get, oops, I kind of put them on the wrong spots. No, that actually works. You know, so that when you break things apart, you're going to get carboxylic acid, PO4, and an amino alcohol, because you're actually going to get like that, right? And so, I guess what I'm trying to say is, look for the similarities in things, look for the patterns, and realize that all of those are the same, regardless of whichever chapter I'm in, right? Or, for instance, if I take and expand on that one, how is it any different? So this is not exactly, you know, these aren't exactly amino acids, right? But do they have the main functionality of amino acids? Which is, they've got an NH2 on one end so that, you know, when you go minus H2O, you're making that amide bond, a bond OH. And the reason why amino acids are so useful is you can keep connecting them together forever, right? It's kind of like glucose. One of the reasons it's so useful is you can keep connecting it together and make as big a molecule as you want out of a bunch of glucoses, right? Now, if we really looked at what an amino acid looks like, you know, depending upon how we draw them, there's always, you know, that's different, right? Does that make sense or not?
So when you connect the OH and the H2, you're losing two of the hydrogen.
Yes, so you're losing, oops, I didn't quite circle far enough over. You're losing that OH, right? And I mean, if you really want to be technical, maybe I should draw it like this, because you're really only losing one of the hydrogens there, right? But if you can learn to recognize those two reactions, that's the glycosidic reaction, right? It's the same reaction used for lipids. It's the same reaction used for amino acids. It's the same reaction that half of chapter 24 is on, and it's going to be on the final. Jess?
Okay, so if you're using that OH, where do you get that O from?
Which O? Oh,
And
crap.
glyphosate.
That's just me not paying attention. Man, someone's paying attention, though. Even sick and feverish. Oh, I should also point out this reaction shows up in the nucleic acid chapter too, because we're always removing water from stuff. It's really easy.
And this is the dehydration.
Yep, so notice it is the reverse of the previous one, right? So that's one set of reactions, hydrations and dehydrations, right? The other set is whether you're, you know, you have a double bond on something, and we don't really care what. I can add plus H2, right? I can add plus Br2. Makes the exact same process, right? Meaning I add a hydrogen on each side of the double bond, or in the case of bromine, I add a bromine on each side. And we can even go further and point out that this can be cis. I don't care if we care. I guess we don't care if it's cis or trans at this point. And then, of course, the opposite reaction is either minus Br2 or, we don't really use that one, but minus H2 to add double bonds to stuff. I mean, really we don't do that, but it's the same process, right?
So this, what was the original one that we learned that this one's like when you break double bonds? Is that
This is what we called addition reactions, right?
you know what I mean though?
Yeah, it was way back in chapter 20. Is that what you're saying?
Yeah.
Yep, way back in chapter 20. In fact, we added hydrogens, we added chlorines, we added water, we added, what else did we add? There's one more I'm thinking of. Water, hydrogens, bromines. Pooh, can't remember the last one.
Dehydrogenation.
So this
That
would be
where you have
hydrogenation.
That's you would have the right side, the product side, and you want it to react.
Right. And so if you can just kind of remember that it's always a back and forth. And the D part makes sense because it's, you know, taking it away, right? To make a double bond. One of the problems is if you take saturated fats and make unsaturated fats by this process. So if we take a saturated fat and we make unsaturated fat, and see this ties everything together to me. So of course, you know, you're doing that reaction, right? Plus H2. I don't know if I have too many carbons or not. You can either get, oops, I'm sorry, dehydrogenation, take away the hydrogens. You can either have it like that, or, let's just, meaning we can make cis, right? Or we can make trans. So one of the reasons, or one of the things that people used to do more of, now it's pretty much verboten, is they used to take saturated fats. If they wanted to make it unsaturated, then they would simply take away the hydrogens and do a dehydrogenation process, and they'd make trans and cis fatty acids. But what do we know about trans fatty acids? Yeah. And so one of the bad parts is when you do the reaction, it's very hard to control whether you get cis or trans. You get a mixture usually. Now, as we get smarter as chemists, we can probably do a better and better job, but overall, you're going to get trans. And so one of the things you see on labels a lot of times is no trans fatty acids. Well, I have to be honest, 90% of the things that say no trans fatty acids are bullshit anyway because they never add them in the first place. But there are certain cases where I think they've actually just stopped doing it for the most part and have found better ways to do it. But you know, you really would get a mixture of trans fatty acids in there. And why is trans bad and cis good? Or what else? See, this is how the topics segue. We're talking about reactions, but we can talk about cis and trans also, right? So
Cis increases the HDL, high density lipoprotein, and lowers the low density lipoprotein. And trans increases the low density lipoprotein and decreases.
somewhat. I think there really is.
So I didn't write that down, so I don't know what
I
it said.
think that's a very small. I think the main reason is really that this is not found in nature. Not
Right, it's man-made, mostly man-made.
meaning, and I really shouldn't say not found in nature. Mostly not. There are actually some trans fatty acids that are actually really good for you. They're the ones that are found in nature, which makes kind of sense. But it's the non-trans fatty ones that are bad. And also these tend to have, let's see, which way is it? Trans have lower or higher boiling points. They must have lower, if I remember right. No, other way around, probably. But, you know, and so this is how, you know, all that we're learning, if you look in these chapters, is cyclic. You could actually take any of these chapters and almost read it from the back to the front and have as much information gained in it. Not all, but a lot. So that covers those reactions. Here's one of those broad concepts that we introduced in this chapter, but actually takes place in all the chapters. What is a metabolic pathway?
I was gonna ask you, like, actual.
What we generally mean is that we start with a single molecule that, through many reactions, becomes what we want. And that's, I'm sure Todd would look at me and go, Jay, dude. And I'm like, you know what? As a chemist, that's what it really is. It's a bunch of freaking reactions chained together. It really is. And the end goal of it is either make something specific or to extract energy, for instance. And I like to many steps. So there's many reactions. The general idea with metabolic pathways is it takes more than one step usually to get to where we're wanting to go to. Let's see, beta oxidation is 5 steps. And then they just repeat the same 5 steps like 500 times. And what, citric acid cycle, is that 14 or, no, maybe I'm thinking, crap. One of them is like 13 or 14 or something, you know. There's a different number of steps for different things. I have to be honest, one of my, I won't say weak points, but I never bother remembering too many specifics. I try to remember general ideas and then that apply to many things, right? Like, it's kind of like saying, you know, I've memorized what 2 times 2 is, but I'm not going to bother memorizing what 125 times 217 is, right? Because once you understand 2 times 2, you should be able to understand the harder math problem, right? Same thing here. If you understand the broad, vague concept of a metabolic pathway, then you ought to be able to apply that idea to other things. And so that single molecule we usually, or quite often will say, is a precursor, or the mother, and then we usually consider the end products like daughters. Let's see. So the idea is a metabolic pathway.
Precursor and parent are the same thing.
Yeah. I mean, oh, and parent too. I don't know. I've seen it referred to in all different ways. I think biologists tend to use mother-daughter. Chemists tend to use precursor. Some people will use parent.
So
I don't know.
And the enzyme would be the many reactions?
Well, no. The enzymes are what happens on the arrows, right? And so if we wanted to actually maybe make it a little bit more detailed, we could say something like this, right? And this should start looking familiar, right? Here's enzyme 1, enzyme 2, enzyme 3. See, this is actually also in chapter 30, right? So we introduced it first in chapter 28 on lipids, and we're pretty vague about it because we hadn't even talked about what an enzyme is. But now you can go backfill. You can take what we've learned in chapter 30, reread chapter 28, or relook at chapter 28 and say, oh, this makes sense. The 2 examples in the chapter is, of course, the eicosans
So A would
and
be the
cholesterol.
and B would be the daughter.
Really, B, C, and D would be daughter products, meaning they all originate from A. Cholesterol. So, you know, in this chapter we have eicosans and cholesterol as the examples, right? I don't think in the lipids or in the amino acids chapter we had any examples, and there are some specific examples in the enzyme chapter, but we didn't really focus on the actual specific examples. Those are more for illustrative purposes, but it did talk about, like, you know, glucose, making glucose 6-phosphate and stuff like that. But see, if we start throwing in some stuff, you know, from chapter 30 in here, what would feed forward and feed back look like? Do you remember the difference between feed forward activation and feedback inhibition?
Yeah, feed forward is inhibiting, feed backward. Inhibition is when you're moving too much of something and it feeds back to slow down the process.
Right, that's an inhibitor for that first enzyme, right?
Right.
Because if I slow down the first enzyme, then I make less D in the end.
Right.
And then, so that's feedback, right? Feed forward says that, for instance, B might be an activator to make more D, to speed up the process, right? So feed forward activation, feedback inhibition. And I always mean to ask Todd this or do some more research on it some year. I wonder if there is such a thing as feed forward inhibition. I'm not sure why you would ever have something that, you know, you're making one thing of it and then you want to slow down the next step. Doesn't biologically make sense, does it? But I could see, I'm guessing that in more complicated regulatory schemes, you have a lot more arrows floating all over these charts, right? And you also have a lot more steps in between sometimes too. So, you know, like I was kind of mentioning, when we talk about some of these theories, we try to bring up the general basic concept. It's like saying, okay, kids, today we're going to learn how to add and subtract numbers. We don't bother telling you that, well, after adding and subtracting numbers, you better learn about how to do it with fractions, decimals, and, you know, and all sorts of other things, right? Variables, stuff like that. That's one, if you can understand basic addition, then addition with fractions isn't much more complicated than addition with just normal numbers. A couple more rules, right? A little bit more complicated. Same thing with a lot of these ideas. You can understand the basics of feed-forward activation and feedback inhibition. If there's a more complicated regulatory scheme, you would go, ah, it's kind of like feed-forward activation, but it's different because we have a different goal, or we want something else to work better. And these are also important because if you look at, for instance, actually I should point out, well, see, this starts tying in, and we can kick back to our whole topic on atherosclerosis. That might be how it's even spelled. I got pretty good after it, after a while. These topics come up, that's, well, go ahead.
Starting component for
Steroids? You're thinking cholesterol. Remember,
I was thinking of
arachidonic acid,
Oh, like that.
the spider one.
Yeah.
If you called it the spider one on a test, I might actually even give you credit. I don't know. Depends.
There's no guarantee I'm gonna spell it right.
Oh, there's no idea, no way I'm going to actually check to see if you spelled it right. If you starts with ARC and it's not kind of, and has a donic in it somewhere, you know, it's kind of like when I talked about scientist names. It does make me a little sad when people totally butchered a name, but it was pretty close to the, you know, a lot of people for Huygens, they called him Huggins, which is okay, you know, it's kind of spelled that way. You forget the Y in there, but, you know, I accepted it, right? You know, Schrodinger, I had a lot of butchered things. They usually got the dinger part right. But I guess getting back to this, atherosclerosis is an example where a lot of the drugs used to treat it are either inhibitors or activators for certain processes in the body, right? Some of the drugs inhibit the uptake of fat and lipids. Some activate the excretion of fats and lipids, right? And so that basic idea of how enzymes are controlled is also the basic foundations for a lot of modern medicine, which is simply trying to find something. Why does aspirin work so wonderfully well to stop headaches? It's an inhibitor for the enzyme that catalyzes whatever reaction produces the cause of headaches. And so you take aspirin, blocks that little site, binding site, and boom, no more headache because you're not making the molecules that cause the headache, right? Why is ibuprofen good? Well, it activates a process that causes or reduces swelling and inflammation, right? It probably actually inhibits whatever molecules normally cause the swelling and stuff like that. And so all of these things cycle back. I think if you were to, after reading chapter 30 and doing enzymes, go back and reread chapter 28 and 29 with that idea that all of this is really tied together, you start to see the big picture, right? But you can't do that at the beginning. I sometimes think that, I feel like sometimes we should teach everything twice. That the second time through it makes a lot more sense usually because you've got a big picture to kind of put things.
Going from like studying wise, going from chapter 30 and upwards.
Yeah,
Because when I start from chapter 28, I'm like, I don't know. But when I start from chapter 30, it's like I flow.
30's fresher in your brain and
Well,
I mean 30.
Because that's a lot of biology too.
Yeah, 30 is a big concepts one, and part of the problem is you lack the concepts when they talk about some of the stuff in 28 and 29. And so, yeah, tying it all together is good. Okay, again, we kind of got off topic. We talked about metabolic pathways. What else is in here? Oh, well, there's a bunch of specifics about eicosans, like why should we know what arachidonic acid is?
That's the same component.
Yeah, that's the starting component for one of these, right? So, we've got arachidonic acid, right? And that also even ties into, what do we know about arachidonic acid? It's really an omega-6 fatty acid, right? What does that omega-6 mean? One, two, three, four, five, six. Yeah, between carbon 6 and 7. Now, that's not to say, and I know arachidonic acid has more double bonds in it and stuff like that. I don't care. The key is that it's an omega-6 fatty acid, right? And I guess the main thing to realize is that that's talking about a specific double bond. I'm never going to make you memorize the structure of anything, right? You better be able to recognize it. You better be able to build it from its parts. But memorize,
So, I have a question.
Mm-hmm.
If you ask us to give us the definition of that arachidonic acid, and we like talked about like it's the starting components of the thermoxins and all that, are you gonna give us the examples like the thermoxin, whatever, however you pronounce them?
That's a really good question.
Because,
How I phrase the question.
Yeah.
It depends on what point I'm trying to get. If I want you to say arachidonic acid is the parent molecule, I might say, why is arachidonic acid important? And you would say it's the starting point for making all these other molecules. Or I might say, what's the relationship between the two? There's so many different ways to phrase the question. I hesitate to tell you one specific way, because it really comes down to whatever I feel like doing. Yeah, you have to know that.
Starting component for the allergic reaction tissues inflammations,
Yeah.
or like it.
Some basic knowledge, right? That this is the parent molecule. It leads to all those others, right? Thromboxanes. Yeah, I was going to say prostacyclins. Probably being familiar with the words and being able to come close to what they're called prostaglandins. And the last one is leukotrienes. And knowing that these are what is responsible for most allergic reactions, right? Swelling, itching, etc. And it's also, one of them is the trigger for a heart attack.
Oh, that's fun.
And so the key here is to recognize that these are all daughters, right? And heck, if I were so nice as to actually even, put it in, you could actually be expected to not necessarily memorize it. I told you don't memorize too many specifics, but, cyclooxygenase. You ought to be able to clue in on that ASE ending and tell me that happens to be the enzyme. And then the other one is, to make the leukotrienes one specifically, it's a lipoxide, and I know there's not two O's in a row, I'm guessing. I don't care, I'm not trying to spell it.
Put it on the first time you did it, yeah.
I probably did put two O's. Well, because I say lipoxygenase, so there's two O's, right? It's
That's
not,
probably what I'm gonna do, honestly.
and I'm not going to take a point off. If I took points off for spelling and gave you, then every time I wrote my notes, you'd get like +10 that day for just showing up and pointing out all my spelling mistakes. I had one girl one year, she didn't do so hot on chemistry, but my God, did she find the typos. Still didn't, it wasn't enough to save her grade, but I mean, she'd get like 10 points extra credit on everything.
You could get points for finding errors.
I've told you that before.
Well, I didn't know like spelling errors and stuff.
Oh, any type of error counts.
Really? Because there was always, okay. Because I find a lot of.
How else do you think they get fixed? If there's a worksheet with spelling errors, a lab with, like this new lab, this chapter, the one we just did, my God, probably has 50 spelling errors in it because it's never been done before.
Which one?
I just kind of laugh at it and don't see anything
Is it
about
one
it.
that we got?
No, I actually usually keep track. It's the one that we finished up in class today and started on Thursday.
So another was the one that I got that did I did finish.
Yeah, and you should finish the lipids one too, since that was technically due last week on Thursday. Be good if you actually had it done and just turned it in. I forgot to turn it in. Okay, but are you seeing how all these topics start getting tied together? And
It's just
it really is almost impossible for me to tell you what to study on some of these, because if I tell you exactly what to study, then I'm just teaching to the test. And so that's wrong. Certain chapters I don't mind to a certain extent teaching to the test, because like reactions, I really can tell you exactly. I guess I could probably list 500 questions for this.
Okay.
So anyway, going down on this, other things that you should remember probably for this sort of topic is treatments, right? Meaning your book actually literally goes and says there are X number of treatments for this. I don't even... Yeah, there's the statins, and there's a whole bunch more in there too. It talked about NSAIDs, talked about COX-2 inhibitors. At least be familiar with that terminology.
Can we just have at least one example of them? Like if we
I
were
always,
statins,
I always tell you to have one specific example in your head of
right, and
everything.
then statins.
Then if you know the statins, you can do that. This one doesn't have so many treatment options, sorry. It's the cholesterol, atherosclerosis that has all the, 6 treatments listed, right?
Yeah.
But this also does talk about how, for instance, aspirin and drugs that are similar to it are called they're COX-2 inhibitors because they stop the cyclooxygenase. And that kind of makes sense if you think about it. COX-2 sounds like cyclooxygenase. And probably 2 is, there's different receptors probably, or different places that you can try to block that. You can either act as an inhibitor, like allosteric regulation, right? Where you actually don't bind to the active site, but then there are the other way to block those types of molecules is you physically bind to the active site too. And so going back and taking what you learned in chapter 30 about allosteric regulation, active sites, inhibitor activation, things like that, and going back and applying it to and rereading the stuff about the statin drugs and various things, and the drugs for their arachidonic acid, kind of starts to make sense, doesn't it? Meaning it makes more sense. You've got that framework to hang it up on. And I don't know if it's just that this book makes a poor choice in the order it covers things. I don't know how a biology textbook covers it, if they just cover enzymes before they cover all this stuff. I think part of the problem with the chapters, the way they do these, is you'll notice if you look at the carbohydrates, lipids, amino acid chapter, they have a part on structure and basic properties, right? And they try to give you a couple specific examples, but the specific examples don't have a very good framework because you haven't talked about metabolic pathways and even what an enzyme is. And so, it's easy for me to go, oh yeah, notice that they've got enzymes written on the arrow, cyclooxygenase and lipooxygenase, right? You know what those do. Well, you do now. But back then when I first said it, maybe not. So I should remember to make a big issue of that. Maybe we should even have a... I don't expect you to know that oxycyclogenase, what reaction it specifically catalyzes and what step. But I would expect you to say one of the ways to decrease this is to block the enzyme responsible for, turning arachidonic acid into thromboxanes. Or the other big way to fix this is this is also going back to this. Why did they tell you not to have too many omega-6s in your diet? The more omega-6s that are hanging around, the easier it is to make that stuff, right? And have an overreaction to it. Why do they want you to have more omega-3s? Because they're the precursors for a set of molecules that have less severe reactions usually, or less severe consequences or outcomes. Meaning they probably both lead to something that causes swelling, but the arachidonics will cause too much swelling, whereas something from an omega-3 would cause a lot less. So, there's lots of things like that that you can go back through and kind of decide on. Let's see, do I have anything else? I said know the enzymes, omega-3 versus omega-6. Have an example of what the local hormones do. We kind of answered all that stuff there, right? Next on that list is hydrophobic, hydrophilic. I'm not worried about spelling here. I'm going to try. Heck, I've already reached my limit. But what we will do here is give you guys a chance to talk about hydrophilic, hydrophobic for a second. Where is this stupid mouse? I think it's recording again. I don't really care if it is or isn't. People that are here will definitely get it, and people that aren't, I don't know if they'll even bother watching this, because we're going to ramble probably at the rate we're going for at least another hour, right? Hopefully it's helping. I hope that having this stuff refreshed in your brain. I think it would be better if people had put in a couple days of studying. See, that's the trouble. Having it the exact night before the test, not the best time. Having it too early when you haven't studied, not the best time. It's hard. So it probably works best if you've studied a little bit, have some questions, or at least have enough stuff stuck in your brain already that when we piece it together, it makes sense. Because like
that's how I'm right now. Like I've like gone over everything. I like kind of understand it. I just don't know how to put it together. But
good. Then that's how it's.
What's going on right now is it's actually coming together and actually understanding it.
See, notice that hydrophobic crops up in chapter 28, 29, and I don't think we mention it so much in chapter 30, to be honest, but it comes up in chapter 29 in at least 2 places. And so here's the key. You can understand what hydrophobic and what makes something hydrophobic and something hydrophilic, then all the different cases of it are just special examples that should go, oh yeah, that makes sense, because you've got that basic understanding, right? And so what makes something hydrophobic?
Hydrophobic is in water. They're insoluble.
Yeah, it tends to make things insoluble. This tends to make things soluble. So the key here is to realize that this basically is things that are alkane, or any of its incarnations, meaning mostly things that are just carbon and hydrogen. Whereas things that are soluble tend to be things like alcohols, carboxylic acids, amines, amides, salts, meaning things that can form hydrogen bonds or dipole-dipole, whereas this is primarily London dispersion forces, LDF. And I guess technically we should throw in ion dipole in that, since certainly ions are very soluble, right? And so, you know, if you can remember it this level, then if you have a picture, no matter what it is, you should be able to come up with something, right? That works well for something like that, or if it's drawn like this, right? But does that work well for, oops. I think there was supposed to be an extra CH in here somewhere. Not too worried if I get it exactly right, because you get a cheat sheet for that, right? Hydrophobic or hydrophilic amino acid. See, heads and tails doesn't help so much on that, does it?
That top part is hydrophilic and the bottom part is hydrophobic.
Well, really, this part is hydrophobic.
Yeah, and then that top part is hydrophilic.
These parts don't count.
Why not?
Because, I mean, if we're talking about a single amino acid, yes, those things are soluble. That's why amino acids can be dissolved in water, right? But remember, when we are talking about enzymes and stuff, we're talking about lots and lots of amino acids stuck together, right? Right. But notice when we string the amino acids together, and I'm going to go to another page just because I didn't leave enough room. When we do that, what we have is something that looks like this. because we're stringing them together, right? Now imagine that instead of just 3, this is so small, meaning the ends don't really count if you've got 1,000 of them strung together, right? And so when we're talking about hydrophilic and hydrophobic, this is what determines hydrophobic and hydrophilic, meaning for amino acids it's really the R groups, right? Because all of these amides, that's part of that backbone, right? Or that's the part that's connected and repeated over and over and over again, so we call it a backbone. We're going to come up with that same thing when we talk about nucleic acids. We all know that nucleic acids are important because they have what? You know, G, T, A, what's the one I'm missing? C, and U, right? So that's the part, those are like the R groups of amino acids. The backbone of nucleic acids, we'll learn what that is too. That's got a whole bunch of other stuff. That's where the deoxyribose and ribonucleic acid part comes in, right? And so notice that we don't care about for the average amino acid because those are used up making that backbone, right? So what determines whether an amino acid is hydrophilic or hydrophobic is just the R part, right? And so that's a part where, see, if you can remember what makes things hydrophobic and hydrophilic, then whether we're talking about things like this or things like this or even more complex molecules, we know what parts. I mean, if we go and draw a triacylglycerol or, you know, something, or here, we'll make a phospholipid. So there's an O, P, O, NH3 plus, O minus. Where's the hydrophobic and philic parts? You know, I'm not going to be picky. If you included that in hydrophilic, that's okay too. Really, an ester group is not terribly hydrophilic. But that PO4 and that NH3, and these tails are, of course, the hydrophobic, right? And probably, if you really look at real structures, like if you pull up the internet and just type in phospholipids, you'll see that a lot of times they'll draw it like this. You know, show the hydrophobic tails like this so that you can get that idea that, you know, there's your sperm. Or since we're drawing phospholipids, there's your double-tailed sperm, your mutant sperm. Meaning, there's all sorts of different ways to draw it. I found interesting in lab is I simply asked what amino acids are in casein. Well, you have a picture of casein, and a couple people asked me, what amino acids are in casein? You got a picture, you got a cheat sheet, you need to make sure that you can translate a picture to the information that is required, right? That's another thing here. You have to be ready to convert pictures into structures. What's wrong with this? Because I would say I get this for about half my tests when people make triacylglycerols and so on. You can't have a carboxylic acid functional group part on both sides, right? The trouble is when you look it up in the cheat sheet, they draw these the wrong direction, right? So if people just nonchalantly connect them together without actually thinking about what's occurring in the reaction, they put a carboxylic acid functional group on both ends. I would say about 3 people did that on their homework. Well, I mean, so this is wrong, right? This is right. There's just nothing there. Because it just, you know, is a CH3 group. See, that's why I'm saying where if you can understand this reaction, if you say, I understand the hydrolysis, or dehydration, sorry. See, the trouble is that on the cheat sheet, they're drawn the opposite direction, so I always have at least one person that's not paying enough attention and sticks the card that on both ends. I gotta be honest, it should look fucking weird if it's on the wrong end. You should be looking at it going like, whoa, something's not right. Meaning, if you practice drawing these enough, if you've looked at them enough, checked them out enough, and there's a whole lot of places, you know, you have to draw them in your homework, your pre-labs and stuff, then you should know when it looks weird, right? If you're the sort of person that, after doing the homework, then on the pre-lab says, oh, I'm going to look up the answer in the book, well, you've lost the whole point of it. I know you can look everything up in the book. Hell, you can Google the answer to 99% of this stuff. The whole point of 90% of the homework and labs is, can you do it without doing that? And if you can, you know what you're doing. And if you have to look it up, you got to be making that mental note that says, okay, I had to look up how to draw a phospholipid for the 3rd time this chapter. And like, if you have to do it, if you have to look up how to draw a phospholipid on the study guide or study, you should be going like, okay, this is the last time I can look it up, because I ain't going to be able to look it up on a test, right? So, you know, when you're doing things like those labs, look at them critically and say, okay, yes, I know the answer is written down somewhere. I can Google it, whatever. That's not the point usually, because I'm a master at Google Foo. I can tell when people Google an answer because, heck, I've usually seen it before, and sometimes it's even the answer I Googled up when I looked it up to write the answer key. Although usually I know the answer too, but you know, and half the time I don't write answer keys anymore because I'm lazy. Jess.
Are you gonna Microsoft Edge input? Because I remember when I connect them, I remember to put plus 3H2O.
No, I mean, if I just ask you to draw a phospholipid, you probably shouldn't write plus 3H2O, but I'm not also going to get mad. Now, if I ask you to write the reaction, you have to put the H2O in there, right? So that was another thing that I thought was funny. So take a look at the labs you got back, which only one of you turned in. So anyway, Aaron, if you take a look at the lab you got back, I don't know if you're one of the people, but I would say 99% of the people, when they did the acrolein reaction, looked at it and said, oh, I just copy it from the front page. Not a single, only one person, I think, or two, put plus H2O at the end of it. Because it's a dehydration reaction, right?
Yeah.
And of that, not a single person put plus 2H2O, which if you try to write the balanced reaction, you should see that you lose 2 waters in it. And so that's what I mean. Don't just copy it. I know you can do that.
I thought that was just
The point of the questions?
Yeah.
No. The questions are not ever supposed to be simply copy something. They're supposed to be, I know how to do this, or in that case, that one might be go look at and you're given that first part, but boy, you better be smart enough and thinking enough so that you go, gosh, there's something missing. Or the number of people on this new lab, like the one you have to turn in for next week, notice there's a bunch of reactions, right?
Yeah.
The number of people that will forget to balance it, forget to put states, forget to put, you know, forget what the heck a complete reaction means. I feel like I should put it in giant caps with bold and then glowing orange or something so that people remember that. But you guys have written enough reactions in this class that you know what a complete reaction is. I'll bet you half the class, unless I remind them or you tell them, will forget to put half the details in because they're just trying to get it done and go. They're not using it as a learning experience. And I know that it's tough to say every question on there is supposed to be a learning experience. Or I'm supposed to, you know, every time you answer a question, you should be asking yourself, why is that question on there?
That's every single question.
You ask yourself why it's on there?
No, I'm just like,
All right, you might, well, I mean, you can go, I have no clue, but, you know, some of this stuff, especially like if you see the same question 5 times in a row, gosh, it usually means I'm trying to pound a point home in your head. Like, I don't think I put it on all of them because I got tired of it, but do you remember doing the organic labs where every single lab had something about solubility and what was more or less dense? Trying to pound home the idea that you should know less dense stuff floats. Not, you know,
Wait,
not,
less than stuff floats?
yes,
No way.
yes.
I thought you were serious for
I
a
think-
second. I was like,
I think she's pulling a leg, but,
No, I'm trying to be smart.
Yeah. that was on every single lab.
right, and
On
same
every
thing
lab.
with, you'll notice every time we talk about solubility and miscibility and things like that, we put in a question about, hey, does this match our rule of like dissolves like, and what does it mean that like dissolves like? Trying to get you to remember that you can't forget LDFs, hydrogen bonds, and all that stuff. The number of people on the last lab, maybe I should mention this in class, but the number of people on the last lab that literally, when it said, does this prove that like dissolves like, said, well, the solids didn't dissolve and the liquids did were miscible. So, because liquids are like liquids, it's true. And solids are not like liquids. Are you kidding me? Check yours and see. If you were one of those people, you shouldn't be giving. Really, just because something's solid means it doesn't dissolve. I'm pretty sure salt is solid and dissolves just fine in water. I'm sure I can find 500 million, okay, let's not be silly, several million compounds that are solids that dissolve in liquids.
What am I looking for again?
We'll look. We just head back to liquid stuff. This is too more.
Oh.
We gotta at least look at the right one we're talking about. Liquids. I just
That's
handed it back
28.
today.
Slide 28 decided to do it.
Might be in the back there.
I dropped something out.
I have too much shit.
Well, anyway, you can look at that later and decide if you really
I just
said that
found
solids and liquids.
Oh, I found it.
So
I
let's.
didn't get a very good grade on it, so I just threw it.
So you should be asking yourself why didn't you? Like here. I'll answer your question. That was a silly mistake. You had a lot of silly mistakes in there.
I know, yeah.
But you did make the solubility one, so I'll give you props for that. Some of the other ones are pretty darn silly. Mostly like not even reading the question really. Anyway, let's get back on topic.
Damn it.
So now we understand hydrophobic and hydrophilic, right?
Yeah.
And realize that it belongs to many different chapters, right?
Right.
And in fact, we even forgot to mention when we were talking about protein structure, it's part of tertiary structure, right? There's 5 things that cause tertiary structure. Can you list all 5? See, that's what I mean. If you know the number 5, at least you
I can
can.
picture it in my head, but I can picture it on my notes, but I can't picture the words.
See, that's what I'm saying. That means you know what you need to study now, right? That's
Yeah.
why I leave the damn study guide blank. I had one person tell me
Actually,
this.
helped me.
I had one person tell me this. You should fill in all the answers for us. I mean, it's like, are you shitting me? I shouldn't even have to give you a study guide because I've already given a normal study guide. This one is just the normal study guide with a bunch of blank spaces in it. You've got the flashcards too. I mean, there's a lot of stuff you can use to.
Flashcards for these?
There's flashcards for every single chapter. I told people that. They're posted on the internet. If you haven't gone to the website and said, let me look at what resources are there to test myself, again,
I did,
not
but
paying attention.
These helped me, so I only printed these because they actually helped me.
I find the flashcards, I almost lecture off the flashcards now because they're like a checklist of don't forget to say this, don't forget to say that. So to me, those flashcards are actually turned out to be kind of useful. At first I thought they were going to be a waste of my time because I hate flashcards, but they make good study things. They also say that, they also list like, for instance, a topic on one side like hydrophobic, hydrophilic, and then they might say, okay, list everything that has anything to do with them. Okay, so going down, this has a section on fatty acids. What is a fatty acid?
Probably shouldn't.
Well, no, that's not true. You need fatty acids to survive. They're called essential, right? Essential usually means something that you have to have to survive. You, yeah, they're basically just carboxylic acids, right? And then there's lots of things you need to know about them, right? Meaning, we talked about omega-3 versus omega-6. And you should be able to both draw an example and discuss them. We also talked about cis versus trans. Again, draw an example and be able to talk something about them. Saturated versus unsaturated. Meaning draw an example of them or be able to recognize them. If I draw a fatty acid up there and I say, what type of fatty acid is this? You should be able to tell me whether it's omega-3, 6, cis, trans, and saturated or unsaturated.
Fats versus oils.
And you could say fats versus oils, but that's more,
Can we just go over fats versus oils?
fats is basically saying that something is solid. Oils are something that's liquid, right? And so that means that fats are usually considered saturated makes them fats, unsaturated makes them oils. So if something is an oil, it generally means it's unsaturated. If something is a solid type fat, then that generally means it's a saturated fat because of how the double bonds in there affect the boiling points and melting points. And I have to be honest, even I tend to have to really think hard about these because at the 0th level, you can simply memorize which is which. But I actually have a picture in my head that says if it's just saturated like this, then all of these tend to line up very like that, right? So that makes these have a high boiling point, and that means they're solids at room temperature, right? Whereas unsaturated, since they have carbon-carbon double bonds, yeah, they can't get as close together, and so you might have them, what, like that? Yeah, that's kind of close enough. That, what? They're actually correct. They're just not pretty at all. And that's okay. I'm not trying to be pretty. So these have a low boiling point because there's not as many intermolecular forces. It's not as easy for the London dispersion forces to act on each other, right? And so that's how I remember which one is a solid and a liquid, because I have to have that mental picture in my head.
So, how do I know, like, going up a bit, how do I know whether fatty acid is saturated or unsaturated?
Well, remember, saturated is just like that. Unsaturated has a double bond. So it's simply whether they have a double bond or not. I have to be honest, saturated and unsaturated, like when I was grading your lab again, Aaron, and I think you were the one of only 2 people that actually got unsaturated, saturated, not reversed completely, is I have to really think hard on that because I just think whether it has a double bond or not, I don't have a very good association with. I have to actually go, okay, the one with the double bond means it's unsaturated because I can add hydrogen to it. I almost have to do this thought process to get what the word unsaturated means, whereas some people just know what unsaturated means. And so, but my theory is if I can kind of do that, well, cis and trans, here's some examples, right? And then trans is the other, well, I drew cis ones, and trans is like this, right? And then omega-3 versus omega-6 simply telling me where I have the double bond, right? 1, 2, 3, 4, 5, 6. So for drawings and stuff, right? And then also, you know, it's in other places too, but how does that affect the physical and chemical properties? Mostly boiling points and melting points and whether they're good or bad for you, right? Like omega-3 and omega-6 don't really affect boiling points, but they do affect which is good and bad for you, right? Omega-3 good, omega-6 considered bad. Or at least excess of one or the other is bad. Certainly you need both in your diet. That's the thing I think that's tricky about nutrition. Anything that you have in nutrition taken in excess is bad for you. In fact, they're starting to show that all those people that take multivitamins might actually be bad for you. That overdosing your body on some of them might actually cause more harm than good. They certainly put a strain on your system to eliminate them. And if you have a decent diet, you're getting enough of them anyway. You don't need 1,000 times the daily dose or 10 times the daily dose. Like if you have too much calcium, you can get bone spurs, right? Not enough calcium, you get osteoporosis. There's always that sweet spot you got to worry about. You know, wonderful, you don't eat meat, so you have less fatty acids and saturated fats in your diet. Well, guess what? You need some of them. You better be getting it somewhere, or you're going to have health problems. I don't know. Is peanut butter considered complete enough? Right. I mean, certainly you need the essential amino acids, right, from it. But I guess specifically you need to make sure you eat enough of the right type of beans and nuts to get, you know, all the essential ones. But is that better or worse than a diet that has a lot of it? I don't know. I mean, it's not horrible. It's, if you have some meat, I don't think it's bad. If you eat a gigantic steak like that every damn night, probably not good for you.
Tastes good though.
Yes.
If it's the right.
I actually find what happens is if I don't have steak for a good long time, or if I don't have greasy foods for a good long time, the first time I do them, my body's like, oh, hell no.
That's my body all the time, so I have gallbladder, so
Oh, yeah, that's right. You're a freak.
It sucks. It's
Gallbladder,
so bad.
brain
Like,
injuries.
Every time I have fast food, I'm just like, it doesn't taste good anymore. Like, I don't want it.
When did you get it taken out?
Why?
No,
It was-
when? Why and why?
You wouldn't have done it. It was like not. It was non-functional gallbladder.
Why was it non-functional?
It's like hereditary. My mom didn't. Hers wasn't working when she was like 20 or so, and I got it. when I was
See, here's where we
17.
need Sarah or Todd in here, because I don't even remember what the hell the gallbladder
I don't know
does.
what, like,
I
I
know you can
remember-
live without it.
it digests the fat content and like it uses bile and it digests the
Yeah,
fat
I remember
content.
that.
And
So basically,
And it's
fatty
just like-
foods don't do much for you.
And I noticed that like a year after, like I noticed that I couldn't eat a lot of things for like 6 months, and then I went to church camp and they had like a lot of greasy foods and I couldn't eat anything. I went home and I was like, I went to the doctor and the doctor was like, yeah, sounds like your gallbladder. And I
Oh.
don't know what kind of test it was. It was kind of like, I don't know, they put a screen right here and they injected
Yes.
something, maybe drink something.
Probably I forget, like, you drink barium or something, and
Something
then
like that. And it like
Oh,
makes your gallbladder.
radioactive. Yeah,
It like
gosh.
makes your gallbladder do something and they can actually see it like not function.
So, do you have to take any drugs to help you with the digestion of stuff then?
No, I just go on a really strict no fat diet. Like I don't really eat too much.
It's tough because fats are everywhere.
I know. Like when I was, because I didn't want surgery too early because I was still in softball. It was my last year, so I went on a super strict diet and I couldn't eat anything over 5 grams of fat. So my mom made every single meal. I couldn't eat anything that my mom didn't make because she knew everything that went in it. And now that I'm not really on that diet, I can't eat anything. Like I haven't eaten anything in the cafeteria just because every time I do,
Basically, eat cereal and salads.
I can't have cereal because I can't have milk. I'm lactose intolerant. It's shitty.
You
I
know,
hate my life.
I'm not even sure your life is worth living.
No, it sucks.
Maybe there's some redeeming
But
quality to
I
it,
love-
but
I
man,
love
no
the-
milk. I
But
couldn't.
I don't even like the taste of milk because it just doesn't like me. So it's just like.
Well, yeah, it's a learned behavior.
Yeah. I don't know. I just even smell of milk. I'm like,
Oh man, I have like sometimes I just crave a glass of milk and I drink milk. I love cereal because it comes with milk.
I like.
Ice cream?
I like ice cream, but I usually eat sherbet, which is good.
Oh well.
Or frozen yogurt. Frozen yogurt's pretty good.
Okay, going back on topic. Now that we learned about, more weird shit about Aaron. Do you want to take a break? I wish I had
Yeah.
snacks to give people.
I have a granola bar.
My problem is I haven't gone shopping in forever, and okay, so we kind of covered all that. And sometimes it's in more than one place in the study guide too, I've noticed.
Yeah.
Mostly because I did a big dump. Okay, compound lipids. How many types are there?
Or
Very good. What are they?
I'm trying not to look.
Triacetyl,
Like a
glycerol, right?
Mhm.
Glycerol.
That's,
Phospho,
um,
sphingosine,
lipids
and glyco. So here's what I want. Now, you can try to remember all four totally by themselves, right? I guess I'm trying to link the ones that I think are, yeah, I guess steroids too, but those are the four I linked together in my head, how about? Meaning, I noticed that I look up at the study guide, and it is actually different than how I did it. And that I would say all three of those things to me are the same thing. Because see, this is glycerol, right? Plus 3 fatty acids. That's when we draw them like this, right? And then to me, phospholipids simply say it's glycerol plus 2 fatty acids plus that PO4 plus the amino, right? Meaning it's the exact same thing on the top two, right? And then the bottom one is where you go to that something that looks a little bit like that, right? Meaning if you pick up on the parts that are the same, then it's easier to remember them, right? And then sphingolipid is even better because it's just sphingosine, right? Plus a fatty acid, plus PO4 and an amino alcohol. And you're given all the parts, so you don't have to try to remember what it looks like. And then a glycolipid is just sphingosine plus a fatty acid, plus a PO4, plus a glyco means carbohydrate, right? Actually, there is no PO4 in this one. And so the key is to look for the parts that are the same and the parts that are different and make some sort of either pattern in your head or, you know, to me, I guess, I don't know. I mean, to me, all those words mean something. And to me, when I see a picture of them, I can almost see the 4 pictures, you know. There's that. Well, the sphingosine one is the one that has a strange OH group on it, and then this part's got a double bond and a bunch of stuff. And then here, we end up having an amide instead of the normal carboxylic acid, but then the rest of it's the same. And then the last one on the glycolipid is still that sphingosine part that's the same. So that part doesn't change. It's still this part that's the same. That part doesn't change. And then the last one is just straight to a carbohydrate.
So on phospholipids, is that mean or mean?
These are carboxylic acids because it's glycerol, right? When it goes to sphingosine, that's where this middle one is that NH. But look on your cheat sheet and tell yourself, do I really need to remember that one of them is the amide and one of them is the alcohol? Not really if you know how to use the cheat sheet, right? So if you practice drawing 1 or 2 of these, you'll pick up on the patterns, right? And you should be able to do it from scratch.
On the board where we have to like combine them to make them into those.
Yeah.
Will you like, does that make sense?
Well, we've already shown that reaction, right?
No, I know, but like, will you put one on the board where it's like, do glycerol plus this plus that plus, and we have to write them on the board?
Isn't that what I just kind of did? I mean,
No, like where we have to write them and you check them.
oh, do you want to practice right now is what you're saying?
Ah,
Ooh,
just to
where
make sure
does
that
the
it's got it
structure,
right.
like the reaction on the structures or whatever?
Yeah, you had glycerol plus
I thought them were all.
palminic acid, oleic acid, like
Well,
stearic acid.
to me, and here's the key. Well, I guess maybe to me, whether I tell you a specific acid or a generic one, the process is still the same. The only thing with the specific one is you have to go and see if it has a double bond somewhere and how many carbons it has, right? To me, the only difference between stearic acid and maleic acid is 16 to 18 carbons and a double bond or something. So I guess if you want to practice something, try glycerol plus PO4 plus ethanol, amine plus stearic plus palmitic. Or if you want another one, try, oops. check it out. She sniffed it. And I have to admit that some of this is better to cram at the end, certainly. But some of it, you should also always be saying, what's stuff I can practice on and off every day? Or on and off, you know, and once I get it, I'll get it. I mean, if you've already practiced drawing all these lipids when we have the lipid chapter, then you shouldn't need to study it right now, right? So that's less cramming that you're doing. If you said, and took that structure cheat sheet part, or that structure practice sheet, and simply said, okay, I'm going to draw one of these, I'm going to fill in one of these every day this week until I get it right. Then you'll figure out which ones you know and which ones you don't, right? But if you try to do it the night before and you have to learn 8 of them, boy, that's going to take away from studying things that are harder to study. Whereas something like that, you can study well ahead of time and have it down. Trouble is, it's hard to do that because it's hard to say, I should study chemistry when you're like, wow, I just finished all my homework for all my other classes. Am I going to study chemistry or am I going to go to bed? Or watch a movie? It's a tough call which one you choose, right?
Yeah. I should do this, but I'm not gonna do what I
And what I often tell people is, welcome to the real life. When you have your 8-hour day job, you realize that it takes you an hour to get ready in the morning, and it takes you an hour to cook dinner, or eat dinner, or something like this. It takes you got to clean the apartment. You quickly realize that on average, you only have a couple hours of free time a day if you're lucky.
Unless you're like me and skip the cleaning part.
Or, for instance, don't have kids if you want any free time.
want kids, but not till I'm older.
So,
Okay. So on this first one,
mm-hmm.
when I put them, when it be, the cholesterol comes down as CH2, 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 OH, OH,
Mhm.
OH. The PO4, when I bring that off of one of those,
The bottom one generally. Although arguably, since you can flip the molecule right side either direction, you could put it on the top and it doesn't change anything.
but then I still got 3 more to put on. So would it be stearic acid and palmitic acid connected?
No, they each go to. So, Josh, maybe you're at the point where you need to think about it like this. To show the connectivity parts, meaning just the words aren't enough.
So then, so my, okay, so this makes sense now. So the ethanol amine connects to the PO4,
Mm-hmm.
and then the stearic acid and the palmitic acid.
Go in one of the fatty acid slots.
Okay. So I just write ethanol amine.
You should practice drawing it, because you don't want to get it wrong, right? I mean, it's up to you, but I think the whole point was to practice drawing.
So F is 2.
Suppose I should find my cheat sheet, because I don't know which ones those are, unless I look it up. Unable. Aw, you piece of crap. Every once in a while it just loses the internet.
On the ethanol amine, on
Mhm.
the OH part, would I just remove that H since there's an O there, or would I have?
Well, what really happens is, when you're writing the reaction out, phosphate really looks like this. And so, for instance, here's your glycerol, right?
Okay.
So here you're losing water, right? So that's why it just ends up being OP, right?
Okay.
Here's your amino alcohol,
So then I would.
and so here's your water, right? So you really just have an O connecting them.
Okay.
See, if you understand the reaction, then you don't have to memorize where the O's go and stuff like that. You can actually just do the reaction, worst case scenario, right? To me, it's great if you've learned it enough so that you can just draw it. But if you have to resort to showing all the parts and showing where the water's removed and connecting everything together, that's actually probably better because it shows a deeper understanding. Whereas I've just happened to have drawn these 5 million times, right? Oops. Although, see if I'm in a hurry, I forget things. And then this sometimes is shown as O minus, sometimes it's shown as OH. I should just decide one way or the other. But it generally loses that hydrogen.
Over the structures in a little bit together.
Well, if you want me to look at it, I'll look at yours.
Oh, yeah. I think that's fine. This is just for the phosphorus.
Assuming you have the right number of carbons, it looks good.
Okay.
Oh, no, you have 2 O's in there for some reason.
I don't know why I do.
And see, that is very easy to just glance over, and so that sometimes,
Would that be right?
nope, see, you forgot. Remember when this part is occurring right here?
Oh wait, that would be
That's
CH2.
CH2OH, right? And that's reacting with an HO to your fatty acid. So notice that you're missing a carbonyl group in there.
Oops, I forgot. Let me see. I remembered not to put it in on the end, but then I forgot to put it in the beginning.
That's why I say being able to directly draw it without showing the reaction is wonderful, but you tend to make more mistakes.
Like that then.
Except you need CH3s on the end, right? You can't just... And then you better look. And if you're going to draw it out this way instead of line drawings, you better count the carbons. That's 1, 2, 3, so that must be, if one of them steric acid, 15, right?
Yeah, and this one would be,
Is palmitic only
15 like
16?
that.
Yeah. Now, you didn't really have to show this extra CH2. You could have lumped that in.
Okay.
But I wouldn't mark it wrong. It's just a little funny looking.
Okay. And then would be plus, would it be plus 4H2O?
When to make this, Bob? 1, 2, 3. We'll try to at least get through this, since this is the older material, so it should be less fresh in your brain. Although for Jess, I don't know, have you watched the enzyme lectures yet from Monday? Do you remember anything from Friday? Actually, we didn't have class Friday. It would have been last week, Wednesday.
No.
So, see, here's where, like, for instance, lipid aggregation. Well, that's just kind of knowing the structure, right? That's knowing about hydrophobic and philic, etc. And then sticking them together and realizing that, you know, it leads to both micelles. It can lead to liposomes. It can lead to lipid bilayers. kept wanting to spell by, B-Y-E. And atherosclerosis. And see, this is where it's hard to decide, you know. To me, liposomes and lipid bilayers are identical. They're exactly the same thing. Todd will be like, no, lipid bilayers have all this extra stuff stuffed in them. And I'm like, yeah, but from the point of understanding lipids and how the basic layer is built, they're the same thing. And so I have to be careful. Sometimes I tend to oversimplify. There are differences, but there's a lot of similarities. Same thing with liposomes and micelles. They have both similarities and differences. And so when I think about things, that's how I tend to categorize them. Certainly you should have a picture in each, and there's lots of little aspects you can memorize about each. But if you sort of understand the basic concepts of the structure and the hydrophobic philic parts, then you'll probably be able to come up with the differences between micelles, liposomes, lipid bilayers, and then talk about atherosclerosis, right? See, for me, micelles are really just fatty acids, which means they have one tail, right? Versus liposomes and lipid bilayers, which are actually triacylglycerols, right? So they're really fats, and so they really look like, I'm sorry, they're phospholipids. Oops. And so that's why they have a hydrophilic head and two tails, because phospholipids have two fatty acids on them, right? And that means that this forms a single layer. Oops. Right? Whereas this has to form a double layer. And so you get that inner core and you get that outer core. And that the outsides are always hydrophilic. Actually, here, we'll just do this. Hydrophilic. Hate will be just hate. I don't know how you can draw hate. Loves water, hates water, loves water on the inside. Oops, that's not a very good heart. Probably is what my heart looks like, though. Dried up lump of coal these days. I keep hoping something will reach down in there and awaken it, but probably it's just going to shrivel up and die. Don't worry. Someday you will be old and bitter, too. Something that everyone look forward to. And then you're just young and bitter. I'd be bitter too if I had no gallbladder and had gotten a concussion.
Then eat shit. Yeah. Sometimes like if I like just bump my head on like the wall and I'm like laying on my bed, I'm just like, oh.
Really?
Headache, I'm just like,
That's sad.
like before you know how it's just like, ow, I kind of hurt now. It's just like, ooh, that hurt real bad, but it like worse than it should have.
And see, lipid bilayers just means that it's the exact same picture as this,
Like
except they make it
membrane.
huge. Right. So they make a membrane. It's just a matter, a function of scale. Plus, this also has cholesterol in it, you're right, and what else does it have in it? Yeah, protein. So, I mean, there is some extra stuff in there, but I also figure you cover it in Todd's class more than I would ever cover it. So, if you can't answer a basic question about what makes in a lipid... Ooh, maybe I should make that an extra credit question. Draw a picture that Todd would give you 10 points of extra credit for, and I'll make him grade it.
Do it. Me and Aaron will ace that shit.
But there are extra parts in it. And so, really, if I say liposomes and lipid bilayers are the same, it's true if you just look at how the phospholipids are arranged, right? And then you can say, well, some of the differences are in a lipid bilayer, it has extra stuff in it, right? Yeah, I mean, you know, it's a really shitty picture, right? And I didn't draw all the extra shit in it, but what I'm trying to say is, in class and in the book, that's about as far as they basically go with it. I mean, if you want, you know, go ahead and draw something fugly like that to be a protein pump. And gosh knows how you draw cholesterol in there, because cholesterol's a pain in the butt to draw anyway. So you draw like, oops, which is something, oops,
Yeah.
oops, like that, and
And
That
then you
one's-
draw 'em in place of the tails too.
Yeah, I know. I'm just saying that if you know, I'm lazy. I guess actually I'm really tempted to put that as an extra credit question because it was something from the book, but it's also something you should know because every one of you has Todd's classes. Except, well, no, even
We all
was that
do.
in Bio 111 or Bio 204?
It was in
What do
probably
I know?
both.
Because Brittany was in that.
It was, yeah, Brittany and JT were in bio last
111.
semester.
So there. It's a good extra credit question. Anyway, trying to stay focused just a little bit. That covers, 3 of them right there, right? Now you can also talk about function. Well, you should be able to talk about a lipid bilayer function pretty easy. This is transports water-soluble things, right? And since this is hydrophobic in the middle, this transports hydrophobic. And see, that idea that these transport shit falls into, or also kind of starts popping up when you notice the discussion of atherosclerosis, right? Atherosclerosis, whatever. See, that has lots of ties in that, we talk about HDL, LDL, and VD, very low VLDL. Low density lipoproteins, LDL. And really, when you think about it, all that HDLs, LDLs, and VLDLs are is they're basically micelles with a few proteins studded on top of them. So they function kind of like, that, or they transport them like that. And then really the difference between HDL, LDL, and VDL is how big they are, right? High density, low, and very low. And then the difference is also their role, right? VDL takes it to, or delivers to the adipose, right? LDLs deliver it to tissue. And VLDLs return to the liver. Meaning, if you can kind of do that, and then if you think about it, you should be able to draw a really crappy picture where, you've got a liver, adipose tissue, fat storage. See, to me, I don't even think of the word adipose, I just go fat. And then this is peripheral tissue. And so then if you know those definitions, or, like I said, have this picture in your brain. Oh, actually, I got these. Oh, I switched 2 of them. My bad. HDL is the one that scavenges. VDL is the one that goes to the adipose. Oops. And you know why I caught that mistake? I remember the picture. And it's a really shitty picture. You should look at the one in your book and probably sketch something slightly nicer than that, maybe. But to me, I recognize the picture. I really do. So I know that the picture goes in clockwise if I draw it like that. VLDL, LDL, HDL. So it goes from low density to medium density to high density, basically. And so that's how I remember their roles. Does that seem weird? Like, I remember a picture better than I'll remember the words and definitions.
That's what I do for my
Also, realize this is page 779. And so, to me, like, I can never remember if HDLs or LDLs are good or bad, right? Which one is good, by the way?
HDL good, LDL
Yeah.
bad.
How do I remember it's good? Because by showing this diagram, I say, oh yeah, that's the one that returns the shit to the liver and cleans up your body, right? It's like a giant vacuum cleaner, and it sucks it all in and takes it back. So that's how I remember HDL is good. So like if someone says, Jay, or we're reviewing and I write down HDL and LDL, and they're like, what do each do? I'm like, fuck if I know. I have to draw the damn picture, and then I'll figure it out. Seriously, that's how I learn stuff. To me,
That's how I learned it from my girl.
they're all very similar, right? And so I've got to come up with some way to do it. And the way I do it is that picture made sense to me because I can remember that it starts off as low density and goes to high density. So that gets the placing of VLDL, LDL, and HDL, right? And then I can kind of remember liver, adipose, and peripheral. That's not too bad. I mean, maybe you can even say, I'll remember liver, adipose, peripheral, so I know the order, lap. That's how I learn stuff too. I'll make up stupid little things like that. Why do you think I have Leo the lion goes grr? Could never remember oxidation reduction until I learned that. Or Buddha. I can never remember which one is up, beta or which one is up, alpha or beta. But I can remember Buddha and I can go Buddha. Oh yeah, beta is up, alpha is down. Because I'll remember Buddha. I won't remember which one is which. If someone asks me off the top of my head, I won't remember which one is which. It's kind of like saying, Jay, is Aaron to your right or your left? I'll be like, right. You know, I almost have to picture it. I think I've mastered right and left, but gosh, when I was a kid, I was really confused. I could never keep track of my left and right hands. But I have an excellent direction sense, though, because I don't remember things as left turn, right turn, left turn. I just draw a mental map on my head, which is why sometimes when I drive places, I can get lost. Mm-hmm.
Yeah, that's how I remember things.
And so, come up with something. Lap makes sense to me now. I won't forget that, right? And I'll remember that it goes from low density to high density. Now, you have to be careful because you could accidentally write them from high density to low density, meaning, that's a 50-50 choice, right? Which direction to label it, but maybe you'll just say start with the V. Maybe lap V will help you to remember. Start with the very low density lipoprotein. And then you don't even have to remember a definition of what they are or what they do. The picture tells you what they are and what they do, right? VLDLs deliver lipids to adipose, LDLs deliver it to peripheral tissues, liver recycles all the crap that's hanging out that didn't get used or was improperly transported. And that actually helps me remember what atherosclerosis is, which is the improper transport of all these darn lipids we've been talking about. So try to link all that information into your head. Simply copying it out of the book and writing it down in that box won't help you organize it. You have to come up with something that will help you decide it. Actually, did I make you guys draw a picture of that? I should.
No, you didn't.
Oh, I should add picture for atherosclerosis.
So, cell membranes, what does that have to do with the biological impacts? Is that just talking about the micelles and liposomes again? That they
Where are you seeing it? Under biological? Oh yeah, that's just an example of how lipid aggregation causes those cell membranes, right? Is that what you're asking?
Oh, yeah.
So, and I mean, a lot of these topics I wasn't sure where to put it. I mean, certainly, if you kind of look at the way the book is organized, it really does kind of talk about lipids being hydrophobic and hydrophilic, and that leads to different types of aggregation. Now, I would have covered it covers liposomes and micelles, but it doesn't give them their own little section heading. But it does give a little section heading there for atherosclerosis and biological membranes, because those are all examples of the biological impact of lipids, right?
Right.
So on the test, if I said, give me one reason why lipids are important, or talk about one reason the book talked about how lipids affect biology, well, here, now you got 4 of them, right? So some of learning is organizing information in your head so that it makes sense. Let's see.
So the
Hopefully that's it, 'cause I'm tired of it. Oh, crap.
Atherosclerosis is like it's metabolic disease, accumulation of lipids in the blood cells that cause.
Not blood cells, but blood vessels.
I have blood vessels like.
Just making sure.
Yeah. And then accumulation, it causes high blood pressure, heart attack, and high blood pressure. Did I already say that?
Yeah.
Blood clots.
Blood clots. Yeah, so you've kind of got that.
So
And
that's
maybe
the
you
definition.
diagram it out. Well, I would say yeah, that's a good definition. That covers what it is and what happens.
And
Okay.
that was for,
That
the long one.
Now, I noticed the next one I have an entire section on cell membranes, mostly because I didn't cover it in class, but if you look at it, it's all stuff you already know. We've already talked about the definition and purpose, right? we've already talked about the general composition, the 4 parts of it. The book does mention facilitated diffusion versus active transport. You could go fill that in, right, and try to remember the difference. Talks about what unsaturated fatty acids versus cholesterol does in the membranes, rigidity versus flexibility, right? The purpose of the proteins is to do the facilitated and active diffusion, right? And then the only other one I see there is it says membrane properties. So what are the 2 important properties about membranes? Now here's what I did when I wrote that section. I said I didn't lecture on that, so I simply went through and I read it. So you can even write, for instance, if you want there, let's see, what page is that on? Let's see. Oh, to act as a barrier membrane must have some special properties. See, that should ring a bell in your head. So it just says they need special properties. Maybe I should write down those special properties, right? It says it should exclude water and it must be hydrophobic. You know, so it's got to be hydrophobic, and it also needs to be, yeah. So basically it has to be both hydrophobic and hydrophilic. It has to have parts of both, right? Next, after that is talking about steroids and cholesterol. Now, general structure is just, I told you don't memorize any specific steroids, but you should be able to draw the core part, right?
The cell membranes, page 770,
Yeah, like 780 and stuff. I mean, I think if you skim through the book, you should be able to answer those questions pretty readily. You know, we said metabolic pathway, main uses for cholesterol, and then 6 examples. Now, here's where you have to ask yourself, is Jay likely to ask you to list all 6?
No.
Probably not, mostly because I told you. Would it be a legitimate test question to say what are the 6 primary uses for cholesterol or steroids? Sure, that'd be, especially like if you read the book, it literally lists them 1 through 6. Anytime a book numbers something, you should raise a little flag and go, aha, I need to know that, right? For instance, I'll give you a hint since you guys are here. In the chapter on amino acids, I didn't cover this, but if you read through the chapter on page 29.8, and it's also on the study guide, so I don't feel bad about asking a question on it. It says that there are 7 uses for protein functions, from structural to support to storage. 807. It's section 29.8. And that's, what?
7 uses of protein.
Yep, 7 uses of proteins. Your book actually numbers them 1 through 7. It's an entire section that I didn't talk about, right? But, well, that's probably because you had a smart student that owned your book. But notice, and this is also something I sometimes stress more some years than not. Maybe this year I'll remember to mention it in lecture tomorrow. But like, for instance, in the carbohydrate chapter, the section I skipped in that, at least a good chunk of it was, what are the 3 primary reasons carbohydrates are important? It was a test question. It's in the book. It's bold-faced. The whole point of the whole chapter is about carbohydrates. The first question you should simply be asking yourself is, why the hell am I studying carbohydrates? Same thing here, you know. Why are you studying proteins and protein functions? Well, the reason you're studying proteins is because they have a huge number of uses. And at the beginning of the chapter, it even lists a whole bunch of things like from spider silk to a molecule that helps prevent blood from freezing in fish that live in the Antarctic to, you know, horses' hooves to, you know, your hair, things like that, to enzymes. And so if you can't tell me, I'm not going to say, I'd say list all 7 protein functions, but if you can't list a few of them, oh my gosh. I mean, if nothing else, enzyme is huge, right? Meaning they catalyze reactions. Structural use is obvious too because there's lots of things for that, right? But, you know, the rest of them, yeah, if you start thinking about it, transport kind of makes sense because you know you have cell membranes, proteins there, right? So see, one of the things I should point out is you guys usually know more than you think you know. It's just that a lot of times you're used to being prompted for something instead of going, gosh, okay, so Jay asked why proteins are important. Well, let's see. We had a chapter on enzymes. heck, we had cell membranes and proteins are part of cell membranes. That must be an important thing. Meaning, if you start thinking about every time you've heard the word protein in my class or Todd's class, you probably can come up with 5 or 6 reasons almost. Probably, right? I mean, that's what I'm saying, where if you come across a question that is not phrased like you know it is, or wasn't asked on a homework question, you probably had to know the information in some other format and just need to apply it. Like, I don't know what a good example of that would be. I asked you earlier, what are the 5 interactions that cause tertiary stuff? Now, I don't know if I ever asked a question that said list all 5, or if I said draw examples of them, or, I might phrase the question, what intermolecular forces are important for protein structure? Well, you should be able to go and say, well, heck, I know that hydrophobic, hydrophilic, that's hydrogen bonding, right, mostly. Things like that, meaning you should be able to connect disparate ideas together to answer questions. And if you're really trying. Or, I also tell people, always have an example of everything. Meaning, why are phospholipids important? You should have an example about phospholipids, right? Why are sphingolipids important? Why is, triacylglycerols important? Why is a triacylglycerol important? Jess?
Because it is.
Well, if you can't think about why it is, think about the picture and go, okay, does the picture jog my brain, right? Go, okay, what else did we call triacylglycerols? We called them fats and oils, right? See, if you can have that linkage in your head, then you can go, oh, triacylglycerols is how we store fats. There you go, right? Meaning you've come up with a reason. So, as a strategy on a test, if you don't immediately know the answer, just start playing word association games with yourself. That's a really good idea. I should mention that. Word association games. I like that. Well, one thing I've talked to Todd about is sometimes I'm more interested in how students learn something than what they learn. I noticed that people are very good at trying to memorize a bulleted list of points, right? But the second you ask them a question that isn't regurgitate this list of points to me, then it gets harder. But certainly the starting point is to remember the list of points, and then you've got to say, okay, this question said, what's an important cause of something? Well, let's see. I remember there's 5 bullet points. Let's see if any of those apply. Or, maybe the 5 bullet, I don't know, these are kind of vague because I don't have a specific question in my head. But, what if I ask a question, what's the function of a lipid bilayer? It wasn't covered in class, but you should be like, well, I know they're hydrophobic and hydrophilic, and I know that means they can keep water out or they can act as a barrier. You should be able to link things like that together and not have to have been given this specific question answer before you kind of have that question. That's the general idea behind learning. When you really get it, you start playing those word association games. And in fact, one of the things I don't think people realize is that there is a critical mass for learning. Like, I think, okay, so in general, I've noticed for chemistry tests, the first test on organic is usually freaking hard because it's all new types of learning, right? By the third test, my test average is usually well into the 80s. And it's not because the material is any easier. There's still a lot of reactions, and in fact, some of them make even less sense than the early ones. But you're used to it, right? You've seen enough of it that you reached critical mass on how to deal with that. Same thing with a lot of this. I'll bet you if you go back and reread chapter 28, and not even read, maybe skim, do something, you should see the pieces pulling together better. Sometimes I've told Todd that I think people learn more the second time through in the review session than they ever learned the first time through.
I'm actually learning and understanding.
Jess would be an example of that. She doesn't learn anything from lecture that I can tell, but the second time around with her, seems like she picks it up. And sometimes she just is a font of just random information. Finishing up this chapter, trying to at least. Categories of lipids, yeah, that's just saying basically, if you can list every type of lipid that we talked about in this chapter, you're starting to get a grasp on it, right? If I ask a question which is, tell me the different classes of lipids, and you're like, oh shoot, there's a lot of them. Meaning, having that classification scheme in your head knowing that there's 5 different types of compounds or 4, the book lists 5. I think I broke it down into 4. That's part of my problem is I disagree with the book. Well, I guess they did break it down into 4. Like, for instance, you might notice that we didn't talk about any of the miscellaneous lipids. We did not talk about fat-soluble proteins and lipoproteins at all. But certainly that should be in the back of your head that you should go, well, I think most people, fat-soluble vitamins are an example of lipids. And you've had nutrition, right? Oh, see, I make the assumption people have had nutrition sometimes when they haven't. But, and then the other one is lipoproteins, which is basically proteins that have some sort of fat or a lipid as a cofactor. And see, now you know what a cofactor means, right?
Yeah.
If I say it way back in chapter 28, you don't know what a cofactor is. In fact, the book doesn't even say the word. But if you put it in chapter 30 context, now you go back and reread chapter 38 and go, oh, a lipoprotein is just a protein and some sort of lipid stuck together. That kind of makes sense. And we know that shit can happen. And it's got a cute little picture of a penguin.
Which page?
The first page of the chapter, which I'm assuming you've read already, so you should remember where it is. Page 765. Do you guys want to go into amino acids and peptides? I guess what I can do is let me mention that, for instance, both of those 2 chapters have a structure thing where it says draw shit, right? Which means not only do you have to draw it, but you have to understand what you're drawing. Meaning, when I say draw a hydrophobic amino acid, not only do you need to know how to draw an amino acid, even though it's on the cheat sheet, so it should be really easy, but you have to understand what the hydrophobic part means, right? So I'm actually asking 2 questions. Can you recognize and kind of know how to draw something? And so the only way you're ever going to get good at that is to just practice it. And if you don't, like if you have a really hard time taking the picture in here and drawing it on a piece of paper, wow, you haven't really tried, thought, or practiced hard enough on that. Meaning something like that needs to be second nature. Any of them. And I'm talking specifically about amino acids because that's kind of what we're transitioning to. The most important things for amino acids, gosh, I don't even know where to start. There's all the definition stuff at the beginning, right? You know, what the functional groups are. But again, I don't think that pointing to the carboxylic acid, pointing to the amine, and pointing to what we call the R group is very hard. Meaning, that's all stuff we've had before. It should be just review, I'm hoping. But, go through and make sure you can draw those pictures. Make sure you understand the 4 different types of functional groups there are. The word essential means the same for amino acids and for proteins, right? Or lipids. And so that shouldn't be hard. Now, something that's new, amphoterism, right? And zwitterions. I love zwitterions just because I love the damn word. So what you have to do is you have to ask yourself and say, if I don't understand it, what's something that can give me a hint about what's going on? So things that I think of when I think of the word zwitterion. Dipolar form of a amino acid, which means there's a positive and a negative on it, right? And see, here's where if you are paying attention, and maybe I shouldn't phrase it that way, but if you've been sort of picking up on the organic chemistry, and you know that there has to be a positive and a negative somewhere on that, right? There's only one place that you can really logically think of. We know that this makes a carboxylic acid anion, right? Meaning if we lose that, we're used to seeing this from the organic chapters, right? And we know that amines love to make quaternary ammonium type things, right? So we know that that does. And so what really happens is the hydrogen on one goes to the other.
For which was this for?
Well, this was what you were talking about, zwitterions, right? Well, that's the same difference. Meaning amphoterism is the ability to act as both an acid and a base. It is also the ability to form a zwitterion, essentially. Meaning they're kind of the same words describing the same things. And so you should be able to say, this zwitterion makes sense because I know when I lose a hydrogen on a carboxylic acid or I gain a hydrogen on an amine, I get negative and positive charges because I'm used to seeing carboxylic acid salts, right? Because I'm used to seeing something like that. And that's where if you have a good grasp of the organic, when you get to this chapter, it's like, oh, zwitterions are easy because I've seen them before, just not stuck on the same molecule, right? Meaning I've seen, this before. Certainly in reactions, you had a bunch of these made. And certainly in a bunch of reactions, you actually made quaternary ammonium salts where you had this, right? So notice that, we're just really saying don't have the Na and the Cl, right? And then how that reacts with an acid and a base, again, that if you remember and simply say, I know that what about positive and negative charges? Opposites attract, right? So that OH must interact with that part of the molecule, right? And so I know that in that case, I lose the hydrogen. Oops, I forgot my R group. Being a little lazy. And then that still stays the same, plus H2O. Or if I've got H plus, I know that's going to react with that, and so then I know I better have form the OH. And so if you break it down into stuff you already know, it gets easier, right? I hope.
Yeah.
And certainly hearing it the second time probably maybe clicks more, because this is exactly what I said the first time. It's just the first time you're probably still back at stage one going, oh my God, it's got a positive and a negative, what the hell? And if you read the book and kind of go through it, what you have to do is say, look at the book and go, how am I going to remember that reaction? I got to be honest, would I, if you had said 10 years ago, drawn it up there and say, Jay, what happens? Would I have known what happens? No, I had to teach myself to remember that opposites attract. Sorry, your hair is like. So.
So for the base, it just loses hydrogen.
Well, for the base, that hydrogen reacts with that OH minus to form an H2O.
Okay.
And so then it loses the positive charge, right? And here, it can't form water, so it just forms the original OH. Oops, that should still be a plus. And so that's where the zwitterions in that dipole are important. Now here's the key. If I said, draw the zwitterion of tyrosine, what changes in this picture?
The R.
Yeah. So I've got 20 pre-made
So
test questions because,
you just have a tyrosine part on the
yeah, there's a reason why I draw R all the freaking time, because it doesn't matter which of the 20 amino acids I show an example of, they're all the same. The only time that the R group matters is if we're talking about secondary or tertiary structure or something. Well, actually not even secondary structure, just tertiary structure. And so realize that if I tell you to draw draw amino acids, they're all the same. The only thing you ever have to change is what the R is. So you have to look in the book and copy it out. Now, do I have to actually show you how to form a peptide bond? How to connect two amino acids together? Think. We know how to connect two carbohydrates together, right? We know how to connect all those phospholipids and that sort of stuff together, right? Connecting amino acids together is the exact same thing. Notice that if I take an amino acid, and notice I tend to draw things sometimes differently than the book, because I try to draw it so that it makes sense. We know that every time we connect two things together, it's minus H2O, right? So what's the only thing you really have to do? Recognize that it's the OH on one molecule, right? Oops. And then that's and one of the hydrogens, right? So that when you make that bond, you get C double bond O dash NH, and then everything else is the same, right? Now, I have to admit, if you don't recognize that it's the carboxylic acid on one and the amine on the one next to it, there's lots of other places they could react together, kind of, or that you could try to make water from, especially if you choose an OH, an R group that has an OH on it, right? But always remember, the part that reacts is that amide backbone, right?
Other ions, and the
Well, this is a zwitterion. This is what would be labeled as amphoteric because it can act as both an acid and a base because it can neutralize both hydrogens and OHs. Basically, think about it as a schizophrenic molecule. We've always before said this is an acid and this is a base, right? Well, there are some rare, I won't even say rare, maybe there's some things that we encounter that are amphoteric, meaning we skipped it when we did the inorganic chemistry. There's actually some metals that can behave as both acids and bases, but we skipped that. Time to take your drugs. Well, yes, see, I was trying to be nice. Actually,
That's like on all my alarms, I like name them, not on my baby time. And then to wake up it says,
makes sense. Makes sense. So anyway, for instance, what I want you to pick up is that whether you're doing carbohydrates, proteins, or lipids, it's all the same. It's all minus H2O. So if you master minus H2O, you've mastered half the final, not half, but you know, a chunk of the final, right? Because you can guess the final is certainly going to be at least draw one disaccharide, draw at least one dipeptide, and draw at least one sort of lipid of some type, meaning whether it's a phosphosphingo or whatever. Heck, I don't even remember anymore which one is asked on the final. It's been so long since I took my own final, I don't remember what's on there. I just know what sorts of things are on there. Meaning, you know, I don't remember which reactions are on there, but I know I give you a list of what ones you should study. I know my testing philosophy is usually don't memorize trivia. Focus on the big facts, right?
So, to study for the final, would it be good to just like review a lot of your tests?
Pretty much.
Okay.
And then, but don't review every part of your old test. Focus on the important parts. And if you're not sure what's important, well, look on the study guide. That should tell you. So anyway, you know how to connect these together, right?
Yeah.
I'm going to hit pause because I need to go to the bathroom again. And maybe